Okay, let's try exercise 4.14. Show that the addition function f from R2 to R given by f of xy equals x plus y is a continuous function. Now I'm going to give two proofs of this fact. First one is going to be sort of fancy proof using something we've done before together with this theorem up here. And then I'll give a little bit more of a straightforward proof after that with some epsilons and deltas in it. Okay, so the theorem I'm going to be using basically says that the composition of two continuous functions is continuous. Okay, and the target of the first function has to be the same thing as the domain of the second function in order to be able to compose them. All right, so my idea is to write this function f as the composition of two functions which I already know are continuous. Okay, and then it'll follow immediately from this theorem that f is continuous as well. Okay, so what are the two functions that I can compose to get f? Well, I'm going to use some of our work from exercise 3.29 in the last chapter, where we considered a quotient map P from the plane to a set of equivalence classes of points in the plane with respect to the equivalence relation defined by, well, 2 points are equivalent if and only if the sum of their coordinates is the same. Okay, so this quotient map P basically takes a point xy in the plane and it maps to its equivalence class, which is a line of slope -1 passing through that point xy. Okay, and then the second function, g, is going to go from that set of equivalence classes to the real numbers, and it's defined by just taking sort of any point in that equivalence class and adding up its coordinates to get x plus y. Okay, basically we're looking at the x-intercept of that equivalence class, of that line. So if you look from beginning to end, we're starting out with the point xy and we're ending up with the number x plus y. So we definitely do get f by composing p and g. Okay, so it remains for me to make sure you're convinced that p and g are continuous, and then it'll follow that f is continuous by the theorem. Okay, well p, since the quotient map, is continuous by exercise 4.5b. Okay, we've shown that quotient maps are always continuous. And then our work back in exercise 3.29 showed that if we take any open set A here in R, in the target of G, then its preimage under G, which, if you think about it, is actually equal to what we called A star back then. It's just the set of all equivalence classes of the form x0 where x is in A. Okay, and so it's a collection of lines which sort of intersect the x-axis at the points in A. And we proved that, okay, if A is open, then its preimage under G is open as well. And that's what it means for G to be continuous. So there we have it. P and G are both continuous, so F is as well by theorem 4.9 up here. Okay, well that works, and it's pretty easy once you have all the pieces, but you might wonder how on earth you come up with that. Okay, so that seems a little mysterious. Let's try again. A little bit more straightforward solution, which has some deltas and epsilons in it. And here's how we start off. Given any point xy in R2, right, in the domain of my function f, and any neighborhood v of the image of xy under f, which by the way is x plus y, in the real numbers. So this is a neighborhood in the real numbers, right? And the basis for the real numbers are the open balls, which are the same thing as the open intervals. So, okay, so if v is open, then we know there exists some basis element in the ball about the number x plus y of radius epsilon, which we can also write as x plus y minus epsilon up to x plus y plus epsilon. There exists some such basis element of the real numbers, which is contained in this open set. Okay, and contains the point x plus y. So that's a good start. And okay, we're going to use theorem 4.6. So by theorem 4.6, it suffices find some neighborhood, we'll call it U, of the point xy in the domain, such that the image of that open neighborhood is contained in this ball, the radius epsilon about x plus y. Okay. And the reason that suffices is because if f of u is contained in this ball, then it's also contained in V, which is what we need to show by theorem 4.6. Okay, so we got to find u. And it's going to be a neighborhood in R2. So how about we look for an open rectangle, right, a basis element for the topology on R2. So we're going to look for an open rectangle of the form, well, let's write it in this form. We know it includes the point xy, so we need the x coordinates to include x, so how about it, sort of be an interval of radius delta about x. All right, x minus delta to x plus delta, and times, and on the y-axis we'll go, might as well use the same radius, interval from y minus delta up to y plus delta. Okay, so we're going to look for an open rectangle of that form as our u, and sort of consider how small delta needs to be in order for f of this open rectangle to be contained in this open ball. Okay. So let's see. Well, let's look at any point in this open rectangle. Okay, so if we assume that we have some x prime, y prime in that open rectangle, well then, what do we know about the relationship between the primes and the original x and y? Well, I guess x prime minus x, absolute value, has to be less than delta, right? And similarly for the y's, the distance between y prime and y is also less than delta. Okay. Good. So that's what we know. I'm getting some absolute values, inequalities going on here. And we need to show that the image of this point is contained in this ball here, right? So you show that f of x prime y prime, which, by the way, is the sum of those two numbers. We need to show that that's contained in this ball about x plus y of radius epsilon. Okay. Or in other words, we need to show that, well, the distance from x prime plus y prime to x plus y is less than epsilon. Absolute value x prime plus y prime minus x plus y is less than epsilon. That doesn't look very good. Let's move this down here. Okay, good. Well, if we need to arrange this, we can use the triangle inequality, right? That's what these proofs always boil down to. Let me see how we can bound this thing. First of all, if we just rearrange the x's and y's, we see that this is the same thing as the difference between x prime and x plus the difference between y prime and y, absolute value. And now I can use the triangle inequality to break this up into a couple of absolute values. Okay, and so, well, I need that to be less than epsilon, so it would be great if I somehow knew that the first one is less than epsilon over 2, and And so is the second one, so that's just epsilon, and we have what we need, right? This expression back here is less than epsilon. Okay. But how can I guarantee that this inequality holds? Well, I just need to have x prime minus x absolute value less than epsilon over 2, right? But I'm allowed to assume that it's less than delta. So I should probably know what delta should be. Right? If we set delta equal to epsilon over 2, then we get what we need, okay? Because similarly, we had that the distance between y prime and y was less than delta, so if delta is epsilon over 2, we get that this term here is less than epsilon over 2, and we're good. All right, so that is the second proof of the statement that this function f is a continuous function.